Welcome to The Explainer. Today, we're jumping right into low voltage and emergency systems. We're going to look at exactly what happens aboard the GF-12000 drill ship when things go catastrophically wrong and the lights absolutely have to stay on.
I want you to picture the ultimate nightmare scenario. Total blackout. Every single main generator is down. You're out there in the middle of the ocean, thousands of meters above the seafloor, with literally millions of pounds of drill string suspended, and suddenly, the hum of the ship completely stops. Now, on most vessels, that is a genuine, unmitigated crisis.
Okay, let's dive into this because you really have to picture the sheer scale of the ship's main power plant. We're talking 42 megawatts of electrical generating capacity. To put that into perspective, that's enough juice to power a small to medium-sized town. Now imagine all 42 megawatts just abruptly dropping to absolute zero. The thrusters, the drawworks, the mud pumps, everything just halts.
But here's the catch. When that massive 42-megawatt plant goes completely dark, a dedicated 1,700 kilowatt STX Cummins emergency generator is standing by to save the ship. But wait a second, 1,700 kilowatts compared to 42 megawatts? Why on earth is the backup so deliberately small? Well, we're going to solve that mystery today. But to really appreciate it, we first need to understand what this ship's electrical system does when everything is actually working perfectly.
So let's flash back to normal operations for a second. Long before an emergency ever strikes, the vessel is generating its main power at a staggering 11,000 volts. That 11 kV is absolutely essential for running those massive 33 megawatt thrusters. But for almost everything else on board, the pumps, the fans, the lighting, that level of voltage is totally unusable. In fact, it's instantly lethal to standard equipment. It has to be tamed.
And that's exactly where step-down transformers come into play. You can think of these 3200 kVA, 11 kV to 460V units as electrical gearboxes. They take that roaring high voltage from the main distribution system and literally step it down to a lower, safer, and much more usable voltage, all without changing the electrical frequency. Because remember, the vast majority of the equipment aboard simply isn't designed to run off 11 kV. It would be fried instantly.
Let's move along and see how this builds. Follow the literal path the electrons take from the massive generators down to a simple light bulb. Step 1. It starts at the 11 kV main bus bar. Step 2. The power hits those 3200 kVA step-down transformers. Step 3. The voltage moves into the 440-volt motor control centers, or MCCs, which distribute power to individual pump and fan motors across the vessel. And finally, Step 4. For general circuits, it steps down again through lighting transformers to a very familiar 230 volts.
Now, we really need to clear something up, because this is a massive myth. In the marine engineering world, 440 volts and 230 volts are officially classified as low voltage. But do not mistake low voltage for low hazard. These motor control centers distribute real, fault-capable current that is absolutely lethal. You can never, ever assume an MCC breaker is safe to work on without independent verification. We're talking strict lockout, tagout, and voltage testing. It demands immense respect.
Okay, so we know how the power flows normally, but let's pivot back to that nightmare total blackout scenario we talked about. The 11 kV bus bar goes completely dead. The transformers have absolutely nothing to step down. Everything goes dark. So what is the actual engineering genius behind having that seemingly tiny 1,700 kilowatt emergency generator? Well, just think about this stark contrast. The STX Cummins generator provides 1,700 kilowatts, which is only about 4% of the vessel's total installed capacity. Now, most people think a backup system should try to replace the main system, right? But on the GF-12000, this massive drop in power isn't a flaw or a limitation. It's a very deliberate design choice. It is physically and electrically isolated in its own separate space so that whatever took down the main plant, say a massive fire or a flood, cannot possibly disable the backup source.
And this brilliantly illustrates the core philosophy of the ship. Think of the emergency generator kind of like a hospital's backup power system during a citywide blackout. The hospital doesn't try to keep the cafeteria ovens and the hallway televisions running, right? It prioritizes the ICU, the life support, and critical monitoring equipment. The GF-12000 does exactly the same thing. Its only job is to prioritize life safety and navigation. It completely abandons drilling operations just to ensure the vessel and its crew survive.
And because it's focused solely on survival, the timeline here is incredibly fast. The moment a blackout hits, within milliseconds, the system detects the loss of main power. Within seconds, that STX Cummins generator auto-starts, and then within a strictly defined time window, critical loads are picked up.
All of this must happen automatically. If an emergency generator fails its scheduled automatic start test, it defeats the entire purpose of the system. In a real blackout, there's just no time to scramble.
So what exactly stays alive on that 1700 kilowatt lifeline? Really just the absolute essentials. Emergency lighting so the crew can actually see and navigate the ship, essential fire and bilge pumps to keep the ship from burning or sinking, navigation and steering so they can maintain control in the water, and of course, critical communications to coordinate the emergency response. That is it. It's proof that emergency power is exclusively about vessel survival, nothing else.
But let me leave you with a really fascinating final thought. What happens if even that robust emergency generator fails? In a true 100% total blackout, what actually still works on this ship without any electricity whatsoever? The answer? Sound-powered telephones. They actually generate their own tiny electrical signal directly from the mechanical vibration of your voice hitting a diaphragm inside the phone. They are a communication layer buried beneath even the emergency power system itself. It really makes you wonder, doesn't it? In a multi-billion-dollar marvel of modern marine engineering, isn't it incredible that the ultimate safety net is powered entirely by the sound of a human voice?